Hi, Stuart here, and today we're going to talk about migrating and modernizing applications to containers or the cloud. So, in a lot of ways, moving your application systems to platforms as a service in the cloud or container systems like PCF or Kubernetes is extremely similar. The things that you need to do to your code base to make those migrations happen happily are extremely similar. And what varies is the plumbing that surrounds the infrastructure part of the cloud. So, for example, for Azure Platform as a Service, you might need some ARM templates to create and deploy infrastructure. For Pivotal Cloud Foundry, you might need a manifest and some other files that define the behavior of your deployables in Pivotal Cloud Foundry. On Kubernetes, you might also need some sort of manifest, typically in YAML, that describes how you want your various bits and pieces that you're deploying to interact with each other. But fundamentally, those definitions are outside of your code, and you need to do them, some variation of them, no matter which cloud or container system you pick. And for the purposes of this talk, we're going to consider containers to be a cloud system. And so we're going to go through and talk about, not all, but at least hit the highlights of some of the things that you need to do to have a happy journey to the cloud. I want to sort of put a stake in the ground. A lot of folks, when they're talking about this subject, talk about migration versus modernization. So you can do modernization of your code base right wherever it's running now. But in order to successfully migrate to cloud or container systems, you're going to have to do some modernization as well. So in our opinion, there's no such thing as migration without modernization, at least most of the time. If your developers and their team were really good and supported by DevOps, and you had very mature practices, and you had already embraced the 12-factor app pattern, which we'll talk about in a little while, you might be able to do something as simple as CF push and have your applications go to PCF, or do an Azure deploy and have your applications go to platform as a service. But it's incredibly unlikely that that's where you are. So just to set the bar, 99% of the time, there is no migration without having to do a little surgery or modernization on your code base. So when Magenic talks about the different stages of maturity of a system as it pertains to moving it to the cloud, we talk about 4 levels. Cloud ready means that you've done some amount of modernization or refactoring to take away some of the more grievous barriers to moving your app to the cloud. So, for example, it's going to be running a compatible operating system version, a compatible version of the runtime, libraries that play nice in the cloud, and so on. You'll have taken away any on-instance disk access. You know, applications should be nicely self-contained with clean deployment barriers. And you should have at least started on some sort of continuous integration, continuous deployment pipeline to be even considered cloud ready. And the test of cloud readiness is, does your application system run when you take all the deployables and put them in the cloud? Now, we're not saying it's going to run well or be stable or secure or anything else, but you can say that your system is cloud ready if you deploy it to a cloud and it runs and passes its functional tests. The next level up on that is a pretty good sized jump. It's cloud friendly. And at this point, you have bitten down on the 12-factor app methodology, and we're going to go through that in a slide or two. And the application systems that you've built are capable of both vertical and, more importantly, horizontal scalability. And they're starting to leverage platform capabilities such as security, high availability, durability, and so on. Additionally, cloud-friendly apps have moved most of their configuration to live in the environment and not be deployed with the app. In other words, you could compile your code or turn your code into a deployable unit and push it to any environment, and on startup, your code will ask the environment for its configuration so that you're not doing a separate build per environment. That's an anti-pattern. The other thing that you'll have done in order to be cloud friendly is any logging frameworks that you have been either rewritten, converted, or set up so that they write standard output and standard error. Almost all cloud systems capture standard out and standard error as the preferred log streams. And writing the standard out and standard error is a good practice because log aggregation systems and log analysis systems know how to consume these streams, and then those can be used downstream by monitoring and management in your cloud environment. The next thing is they really should be stateless at this point, or at the very least have externalized their state to Redis or SQL or some other durable system. They have to start quickly and shut down gracefully without any loss of work. This one is super hard. You can make the app start quickly generally, but having them shut down gracefully, the sort of cloud equivalent of pulling the plug on the server without loss of work, typically requires some modernization and some architecture. And to be truly cloud friendly, they really should use binding to communicate interactions with other services. So if I have a website that runs and it calls a backend web API, then at runtime, through externalized configuration per environment, my website should acquire all the information it needs in order to be able to call that endpoint. In other words, you shouldn't hard code the endpoints for different things. And if you need to communicate other information as well, like ports and protocols, you should have those as part of the configuration as well. Step 3 is really a fundamental shift in how most N-tier applications that were meant to run in the data center work, and that's cloud resiliency. And cloud resiliency is composed of any number of movable pieces, but effectively there are some characteristics that make applications resilient. They don't lose work if the process fails. In other words, on startup, the process will restart where it left off and keep carrying on if that's appropriate. Sometimes it is appropriate to simply return an error and not continue. If you have a highly distributed system, particularly if you rely on services provided by others, whether those are third-party providers or even different business units or within your own organization, you should probably try to implement a circuit breaker pattern so that as you try to call the services from the client side, if that fails, that you fall back to doing some other behavior, and that those circuits should reset. And there's a number of really great circuit breaker libraries. They're available on almost all programming platforms, and they're patterned after Netflix Hystrix. The other good behavior in resiliency is putting something called synthetic transactions or journeys end to end that are used by monitoring systems to not only know if systems are up, but if they're responsive and they're producing sane results. Once you get to that, you can start thinking about other resiliency patterns, such as adopting queue-mediated systems so that your overall system is resilient to peaks in usage. The queue fills up and is drained by workers at a steady pace without any loss of data. You can make those even better if the queues are leased or if you adopt an actor or unit of work pattern. Cloud native is where you should aim, especially if you're starting a greenfield project. You've fully adopted the 12-factor methodology. You have fully drunken the Kool-Aid of whatever the best practices are for your cloud platform, whether it's PCF, Kubernetes, platform as a service, whatever. You should have a fully set of mature DevOps pipelines that are not only capable of continuous integration, continuous deployment, and continuous testing, but are capable of recreating the infrastructure from scratch. So if I go into the cloud and I delete, for example, the staging environment, I should be able to have something in my DevOps pipeline that in an automated fashion can completely recapitulate the environment just as it existed and then deploy all of the deployable units, data, and schema on top of that. That's what it is to be fully cloud native. 12-factor.net factors. So we're going to compare and contrast the maturity in each one of these 12 factors to the 4 levels of maturity of your cloud base in the next slide. But it's worth visiting these and commenting in particular on some of these that are in the key path. Not for nothing, but if you don't have source control or code base, you're in a lot of trouble just to start with. The second part of that is that I should build once and deploy many times. And of course, if we find ourselves having a build per environment, we've done a bad thing, and we should try to evolve away from that. Dependencies. Implicit dependencies make it so that deployments fail when they get to their targets. Understanding by explicitly declaring and isolating dependencies allows your code to be durable. It also documents your dependencies for your compliance organizations. Configuration. We've talked about that a lot, and we're going to talk about it more. Externalize all configuration so that configuration goes with the environment, not with the deployable. Backing services. Treat backing services as attached resources. And by that, I mean that if deployable A needs deployable B, that there shouldn't be any coupling between them other than a contract that says how we're going to interoperate and a protocol that says over what kind of a wire pattern. Build, release, run is this idea of a mature DevOps pipeline where code is built and that build is turned into a release where different builds come together as deployable units, and a release represents the build of each of the deployable units that is compatible with each other. And then those things are deployed atomically as a unit of work to an environment where they run. Processes. We talked about statelessness. We talked about breaking apps into chunks, and we'll talk more about that. Port binding. Port binding is related to backing services very closely in that as part of our configuration, we say, what is the endpoint, what port, what protocol are we going to invoke for this service in this environment? And by not building that information into our source code and instead demanding it from the environment, we have the flexibility to even swap out services that implement the same contracts that may run on different ports or at different endpoints. Concurrency. We're going to talk about this more, but generally speaking, we want to favor scaling out. In other words, creating additional instances of the deployable units over something like threading or scaling up. Disposability. We're going to talk about this a lot more, but basically, each module should start fast and gracefully shut down. And Dev prod parity means that we want to have the same resources and types of configuration in each of the different environments. And that includes, to a certain degree, the underlying resources that are available. So in a container system, dev might be a scaled down version of production, but it shouldn't be running a different version of the runtime, the stem cell, the version of Kubernetes, whatever. Talked about logging. We're going to talk about it some more. Don't have any process at all that doesn't run using the same tooling as everything else does. In other words, don't make administrative tasks and management tasks outside of the 12-factor system you're building. These things should all live in the universe that you're deploying to. So for example, if you have tasks that run on a schedule, or you have one-time tasks that are done, for example, to update a database, they should enjoy the same CI/CD pipeline, the same deployment, the same infrastructure as code as everything else. And now we're going to look at the intersection of going from being cloud ready to being cloud native. The height of each brick is the relative value that you get out of each of the stages. So cloud native apps have a lot of value because they're highly available, highly scalable, highly durable, and they provide the most business benefit. You'll see that inside of each of the big blocks, we've used shading to convey for each of the 12-factor factors, I through XII, the relative amount of adoption for each thing that you really need to do to be cloud ready, cloud friendly, cloud resilient, and cloud native. And you might want to just stop the video at this point and kind of study that. These are relative things, right? But the things that are dark green are things that are sort of must have. The things that are mostly green, you should be fairly far along the continuum. And the things that are very light green are things that you should have at least considered or started on. And it's a continuum. And what programming language, what platform, what operating system, whatever is going to govern the balance between these things. But we wanted to show you from cloud ready to cloud native what your expectation should be in terms of adopting and implementing the 12 factors. Common barriers to moving to cloud system. And again, I'll repeat that cloud systems include platform as a service in the three big clouds, Kubernetes, PCF, other container systems. All of these problem areas will inhibit your ability to successfully operate your software in a cloud. Number one with a bullet is file I/O. For a platform as a service thing, sometimes you're not even allowed to write the file system that your software is running in. Or if you can, they don't guarantee that it'll still be there. If you're in a container system, it's even worse because containers are meant to come and go. They're ephemeral. They're not permanent. If you have file I/O and you just can't get away from it, the low-hanging fruit is to use a shared volume, like S3, Azure Storage, something else. But be aware that file I/O is just not atomic as an operation. So you could be in the middle of writing a file stream to your disk, and if that's interrupted, you could get corruption or rollback, and it didn't happen. If you're able to facade the I/O behind a service, and then you can have a service call which is atomic. It either succeeds or fails. Or you can use queue mediation so that your writes can be retried until they're successful. And if the unit of work doing the writing fails for whatever reason, the directions to do the write are still on the queue because you've implemented leasing on your queue, then that's ideal. Threading is problematic. A lot of legacy code lives in the data center where requesting that you double the RAM on the server or whatever is by no means easy, but doable. It's easier than requesting another server. Typically, developers sort of cheat and achieve scaling by the use of threading. But in cloud and container systems, this is an anti-pattern. Remember, we prefer to scale out rather than scale up. And typically, threading systems, unless they're running a thread, part of the process in a background thread while the foreground thread continues to process, which is okay. It's not great, but it's okay. But the idea is you should try to minimize the threading that's in your apps in favor of scale out. And if there are scenarios where threading is useful, then you should think long and hard about them and maybe consider reducing the overall thread pool and do some experimenting where you are trading the size of the thread pool versus the container size and stability. I should point out that threading should not be confused with async I/O, which is absolutely a good thing on all the platforms that support it. That is, async I/O is designed so that your process isn't in a wait state while I/O is happening, and therefore it can handle more requests. That's actually a good thing, but it's not threading. Monoliths. A monolith is any very large code base deployed as a single unit. So these could be websites, web services, headless tasks, whatever. And the primary strategy is to break these things up. For things like websites, breaking a website into smaller subsites is not always obvious or easy to do. For web services and headless tasks, typically breaking those into smaller deployable units is easier. I just wanted to point out that just because you split a whole cluster of services into a bunch of deployable units doesn't mean you've adopted the microservice pattern. The use of domain-driven design, as pioneered by Eric Evans, is a great analysis methodology for figuring out how to split monoliths into smaller pieces. And if you haven't read the book Domain-Driven Design or any of the subsequent works, I can't recommend it enough as a super useful tool set about how to do analysis and to split monoliths up into pieces. Unfriendly logging frameworks. Many logging frameworks are just a train wreck. They were designed to run on the server. Some of them run okay on virtual machines. Many of them are hideously overcomplicated. They're not thread safe. They cache log entries in ways that are unsuitable for the cloud because, again, the process could stop running in the cloud. And if it stopped running because of an exception and the logging framework had cached the logging messages and didn't write them out, then we'll never know what happened, right? So a lot of these logging frameworks are, for want of a better word, completely unsuitable for a cloud scenario. In a perfect universe, your logging framework should do two things. Should do synchronous writes and should write to standard out and standard error, which are what most cloud systems expect things to be on. If the messages are about things that are okay, they should go to standard out. If the messages are about things that are not okay, they should go to standard error. And if you do that simple rule, then the supporting systems around the cloud can gather, aggregate, and route these messages appropriately to monitoring and management tools, to log aggregation and analysis tools, etc. In-memory state. So this comes in a lot of different and unexpected flavors. When we do code analysis, we often find that languages that support static variables, that programmers have preloaded lots of data into memory and usually lookup type data, but they also, depending on the programming system you're using, like PHP or ASP.NET Classic, they may be using something like session state to remember user-specific data in between calls. Now, a lot of the time, you can remediate that by switching out a provider to Redis or SQL or some distributed state management system. But be aware that if you don't do that, then you have to do another cloud anti-pattern, which is sticky load balancing. What that is suppose I scale my app from one website instance to 3 website instances. If I have in-memory state and I'm a user and I get load balanced to server A and it logs me in and remembers things and I interact with it for a while, and then I get load balanced to server C, I may lose all context around what I was doing, and at best the app would act very badly indeed, potentially corrupting data. You can have other side effects like users suddenly and abruptly being logged out or redirected to the wrong page or whatever. Poor, little, or no logging. This one doesn't require a lot of explanation. As customers ask us to do evaluations of their code base in terms of whether or not their software is cloud ready, and if not, what are the steps or things that will have to be done in order to make it cloud ready, the number one thing that sticks out is that a lot of things that are built in the end tier that are meant to run in the data center have almost no logging. In other cases, they do have logging, but they have terrible logging. We talked about that before. And in some cases, the log messages they do have are not diagnostically useful. One of the questions that we ask developers when we're code reviewing a statement that's written to the logs is, if you read this, could you diagnose and correct the problem? And if the answer is no, it's not a very good logging statement. The other thing, though, is that logging statements shouldn't have confidential information in them, right? Log streams shouldn't contain secrets. So depending on what your milieu is, that might include HIPAA data, PII data, e-commerce data, and so on, right? We want to log what's going on and enough data to put it in context, but we don't want logs to contain security sensitive data. Lost work when processes exit. We talked about this a lot. One of the things that you should do when migrating to the cloud is do a load and stress test, but also do testing where you just kill random containers or random instances and see what happens in an environment where the test framework is going to record if those operations fail. And that is often a good way of finding out whether or not you need to adopt something like queue mediation with leases, unit of work patterns, finite state machines, actor patterns, Saga, etc., to avoid losing work when your process crashes. By the way, if your process loses work when it crashes, it probably did it in the data center too. Incompatible frameworks, runtimes, and unsafe code. So look, platform as a service providers, container providers are super picky, especially about old operating systems and old runtime versions, and in some cases even supporting library versions, because they don't really want you to add security holes or vulnerabilities to their runtime. They're going to insist that, for example, you upgrade your node to a certain version, or you're running .NET version whatever. And they're also going to insist that if you have a specific operating system dependency, that you have tested and run your code on the stable version that the vendor supports, and that you apply that same rigor to any supporting libraries. And in fact, one of the barriers when moving to the code is compliance organizations like security are much more concerned with vulnerabilities when things move to a cloud or container system than they were when they were in isolation inside their data center. Essential that developers embrace the security development lifecycle, and that before you put code into the cloud, that you run static code analyzers, linters, platform analyzers, security standards, any kind of tooling that will tell you about stuff that'll either A, make it not run in the cloud, B, make it run poorly in the cloud, or C, make it run insecurely in the cloud. Thank you very much for your kind attention and time. My name is Stuart Williams.